But before giving you details about what I mean by neuromorphic silicon photonics, so I want to help you a little bit to localize where we are with Emiliano coming from. So we are coming from Italy in Europe, so this is Italy in Europe, and we are coming from a small town that is called Trento. It is in the north of Italy and is actually among mountains, and here you have a view of the town, and the weather in our place is very different from here. So this is me this weekend, and I was skiing in the mountains, and you see all this stuff that is white. I don't know whether you have snow here, but this stuff white is called snow, and we enjoy a lot. So if you like snow, so you can come, you are more than invited to come and join. So let me go back to the lab. So the lab that I'm leading is called the Nanoscience Laboratory. So here you have the website, and those are the people in the lab. So this is Emiliano that is here. And we are essentially covering two different topics, one in nanomaterials for energy and environment and bio application. And the other topic is on silicon photonics or integrated photonics. You can download the highlights of the activity of the lab in the last year. Or if you are interested to know more about silicon photonics, so this is a paper I wrote 2 years ago about my experience in this field in these last 30 years. And since I will leave the PDF of the presentation, so you can ask to Professor Segato, and then you can get the PDF where all the links are noted. So let me go back to the topics of today. So neuromorphic silicon photonics. So I try to convince you that this is a viable platform for artificial intelligence. And before going into the details, I would like to share with you the vision we have and one specific application of our vision. So what we are trying to do in this project that we are running is to merge together two different worlds. So on one side, the world of artificial intelligence, and we implement in photonic circuit this artificial intelligence. And on the other side, the world of living intelligence. And what we are developing are neuronal culture that we grow on top of the photonic circuit in order to make an hybrid artificial and biological network. And the reason why we are doing that is because what we want to achieve is briefly shown in this movie.
Most of our daily actions, such as seeing, walking, or thinking, are governed by the brain. For example, when we read a number, a stimulus departs from our eyes and reaches our brain. This activates a specific neuronal circuit which receives the stimulus and interprets the value of the number. These small networks, called engrams, are the physical basis of memory. Repeated stimuli create memories by strengthening the engram connections. To artificially impress a memory in a neuronal culture, we use light.
So this is what we are doing.
This is possible thanks to light-sensitive proteins genetically inserted in neurons. These proteins control the activity of the neuron and therefore the formation of engrams. Similarly, we mimic biological neurons by using light paths in semiconductor chips.
Those are the neuromorphic structure.
Neural networks that show artificial intelligence. Eventually, we will grow biological neurons on top of the semiconductor chip and use light to exchange information among them so that they can compute or think together. The hybrid artificial biological network could ultimately be used to replace or support malfunctioning brain sectors in pathologies like amnesia and epilepsy. This is the scope of the Backup project, a project funded by the European Research Council at the University of Trento.
So this is the vision that we want to implement by our research. And so today I want to first introduce you about photonic integrated circuits and then show where we are with respect to the actual realization of this vision. So let me start from the first part, that is photonic integrated circuit in order to make artificial network. And the people involved in this activity in the lab are those listed here. And by the way, if you are interested to do a PhD in Trento or a postdoc in Trento, you can contact me since we have many openings, and so you are more than welcome to join the group. And so what we are doing is that to implement this artificial neural network by using integrated photonic scheme and a particular integration in a particular and specific material that is silicon. And so the integrated photonic circuit that we are developing are called silicon photonic circuits. So let me motivate why we are using silicon photonic circuits. So the idea of integrated photonics is to take many different optical components and squeeze all those components into a very tiny circuit. And the reason why we do that are twofold. From the point of view of the performance, so we get very high performance devices because on one side, so we have very efficient devices because they are more stable. So we have no more to align together the different components. We are reducing all the losses associated to pass the light from one device to another devices. And then we get lower noise, lower influence by the ambient. And so at the end, the device that we are producing are very much more efficient than the one realized by discrete components. On the other side, so the fact that we can go to very low dimensions, so this is 1 eurocent, so very low dimension, so, and we use a technology that is widespread, it means that we have lower cost, so low cost in the fabrication of the device, and so we can allow a widespread diffusion of the device that we are fabricating. But the way we fabricate those devices are by using silicon photonics. And so by silicon photonics, I mean photonics devices that are fabricated by using silicon and standard silicon processing. In this way, we get all the advantages of integrated circuit, of microelectronics, meaning mass manufacturability, so we can make volume of those devices that we are developing at low cost and with state-of-the-art performances. But what is even more important is the fact that we can merge on the very same circuit both intelligence, meaning electronic circuit, as well as communication, meaning photonics. So we can get electronic and photonic integrated circuit. And in silicon photonics, we followed in the past the same paradigm to success of microelectronics. As you well know, so microelectronics obey to the Moore's law. So it started in 1948, where the first transistors were demonstrated. Then in 1958, the first integrated circuit was demonstrated. And then today, you have billions of transistors that are integrated in a very tiny electronic circuit. And the very same thing, so we are doing in silicon photonics. So everything started in the 90s, at the beginning of this century, in 2000, where the single photonics devices components were demonstrated. And then in the first 10 years of this century, so we demonstrate the integration of those devices. And nowadays, so we have heavily integrated photonic and electronic circuit. But when you have to develop an integrated silicon photonic circuits, so you have to pass through different steps. So the first one is to understand the behavior of the isolated photonic component. And this is something that we are doing in the lab. So here is an example of one of these micro-resonators that is a microdisc. And so what we do is that we mimic, so we simulate the behavior of light field within this component. So we do a careful simulation of the device. Then what we do is that we take all those devices that we know how they do behaves, and we integrate those devices into a very elaborated circuit. And so this is the design of one of those circuits. And actually here you see many different neural networks that we are studying. And once you have the design, so you send the design to a foundry, and the foundry makes your a chip. And here is an example of one of the chips that we are studying. But having the chip is not enough. What you actually need once you have the chip is to put the chip within a package. And the package is used in order to carry the electrical signal in and out of the chip, or as in this example, so to carry the optical signal in and out of the chip. So you have to do a wiring, and then you have to use a fiber array in order to contact and insert the light signal in your photonic integrated circuit. And those are all stuff that we are doing in the lab. But this is not yet enough. Once you have the chip in a package, you have to put your package chip into a system, like the one that then you actually buy. For example, this instrument here. Here is an example of one of those integrated circuits that we have placed into a package. What you see here, you have everything. So since it's silicon, it's low power consuming, and so we have a battery-operated device here where you have a connector here that allows you to read and write the data into the circuit. And this specific example here is making a quantum random number generator. Not always the circuits are small, the systems are small, so sometimes you have also large systems like this one. And so this is nothing else than a chemical lab integrated together with a part that handles all the liquid, and then the photonic circuit that behaves as a biosensor. So actually here is a sensor that analyzes the toxin content in milk for diarrhea application. And what you see here is that most of the space is consumed not for the photonic circuit, so not for the biosensor, that is a very small chip that is placed here, but all most of the part is consumed because what you have to do is in this biosensor is to move the analyte, so is to move the milk through the photonic circuit. And most of the space is taken by the fluidic action. So this is the integrated silicon photonics. So let me now try to motivate the use of photonic integrated circuit for artificial intelligence. So you know that the brain is a model of power efficiency and performances. So in a brain, in a very small form factor, you have a fantastic device that is able to do extremely complicated and complex computation. And you do that at the expense of a very low power consumption. So the brain is also an example of a very power efficient device. And this is the reason why if you want to lose weight, you have not to think, but you have to run, okay? Because thinking is not consuming power. Let's elaborate a little bit about this power efficiency of our brain. And let's look at the state of the art of the different models in artificial intelligence. And so you now have different models of artificial intelligence that are developed by many different companies, IBM, Google, AWS, OpenAI, and so on and so forth. And what is happening in the last year is the fact that the complexities of this artificial intelligence model is growing at an extreme high pace. And nowadays, so we have artificial intelligence models that are based on billions of different neurons that are working together. And those neurons working together consume a huge amount of power. Just to give you an example. So all of us are shocked by the performance of ChatGPT. What probably you don't know is the power that has been consumed in order to train this artificial intelligence model. So ChatGPT has something like 175 billion of different parameters that have to be optimized. And so during the learning phase, it has been consumed a power that is equivalent to 1.3 gigawatt hours. Let us compare to another system, a human brain. So let's say that in order to learn a human brain, so to put a human brains at high performance, a mature human brain, so you take more or less 20 years, okay? And so let us do a simple calculation. So to teach a human brain to operate as we know, so we take something like 20 years. So the human brain consumes, while thinking, a power equivalent to 20 watt. And so now we have 20 watt, 20 years, we have 360 days per year, you have 24 hours per day, so that means 3.5 megawatt hour. And so this is the power that the human brain consumes in order to get high performance, and this is the power that has been consumed to teach to ChatGPT to perform as you know. And so you see that the human brain is very power efficient with respect to artificial intelligence model implemented in electronics. And this is the reason why we moved to photonics. Here is a very nice review about the application of different photonic circuits for neural networks. So let me try to elaborate a little bit more why photonics is a proper platform or can be a good platform for artificial neural networks. So the first point is light is fast. With respect to electronics, in photonics you do not have the Joule effect, so it's power efficient. In photonics we can use WDM, so wavelength division multiplexing, different wavelengths. Let me work a little bit more about the concept of speed. So this already we discussed. No? So the human brain in the learning process takes more or less 20 years. What probably we don't know is the fact that the typical switching time of a biological neurons is of the order of 1 millisecond, so 10 to the minus 3 seconds. We do have optical circuits that switch in a time scale of few picoseconds. So that means that the time difference here, those data reach the body of the neurons, and depending whether the sum of all the data, input data, are larger than a specific value, so above this threshold, so we have that the neuron is producing an output signal. And so what we want to do is that we want to make a model in order to emulate this behavior. And this model is called a perceptron. So in this perceptron, you have very simple functions that are performed. So what we have is that we have all the data that are input to the perceptron. So then what you do is that you make a weighted sum through the strength of the connection here that are called the strength of the synapses or the weight in the sum. You have a weighted sum of the input, and then through a nonlinear activation function, you produce an output. So let me briefly motivate the reason why. So the sum is easy to understand the reason why we need the sum, because we need to integrate the information that are coming from the different neurons. But the reason why we want to do this nonlinear transformation of the sum is because through nonlinearity, so we can have a better representation of what is happening. So let me give you a very simple example. So here you have a set of data that are characterized by two different parameters. And we want to classify those data in green and red. And so if we have this situation, so we have a very easy situation because we can trace a line and then separate the green from the red. So this is simple. Very simple doing this operation here. So we can separate by a line the two sets. But then if we have a situation like this one, so we cannot trace a line to separate the green from the red. And so the idea is, in order to make those two sets linearly separable, so what we do is that we start from our original set, and then through a nonlinear function, so we move and we transform the set in such a way that now we are able to linearly separate those two green and red points. And so this is the reason why we want to do this nonlinear transformation, is because we want to move data from a situation where we cannot classify those data by a linear separation, a linear border, to a situation where we could separate those data by using a linear border. So this is the reason why we need this nonlinearity. Now a few points that I do need in order to explain you how do we implement this perceptron in a photonic circuit. So the building blocks that we are using. So the first building block is a very simple device that is called a thermal phase shifter. So here I guess that you know that you have a waveguide which is formed by a core where the light is traveling, and then you have a cladding where the light is not traveling. In our case, the core of the waveguide is a silicon channel, is silicon wire. And the typical dimension you can get from here, so the silicon core of our waveguide is of the order of 500 nanometer times 200 nanometers, so very small silicon core. The light is propagating this through this waveguide. Then what we do is that we put a metal wire on top of this waveguide in such a way that the current can flow through the metal wire. But since we have a current flowing through a metal wire, we have the Joule effect. And so depending on the current, so we have that the metal wire heats up, so the temperature increases. And so we have a heat flow that from the metal wire flow through the cladding to the core of the waveguide. And in this way, so we change the temperature of the waveguide. Since the thermo-optic effect, we have that the refractive index of the silicon depends on the temperature at which the silicon is placed. And so by changing the temperature of the silicon, we can change the refractive index of the silicon itself. And so in this way, by injecting the current through the metal wire, we can control the temperature of the silicon, meaning that we can control the refractive index of the waveguide. Now let's go back to our waveguide. So here we have the waveguide, and the waveguide is nothing else than a channel through which an optical mode is traveling. So the optical mode is traveling, so you have the amplitude of the mode as well as the phase of the mode, because the field that we are treating, not the intensity in this case. And so what happens is that now the light is traveling through this region here and then pass where you have your metal wire, where you have injected the current. And through this place here, since the temperature is changing, it means that the refractive index is changing. It means that the phase of the light that is traveling in this phase, in this region here is changed. And so here you see a way that by injecting a current through the metal wire, so we change the temperature, we change the refractive index, meaning that we are changing the phase of the light. And this device is called the phase shifter. And the amount of phase shift is controlled by the amount of current that you are injecting. So we have a tool to control the phase of the light. This is the first basic building block. The second one is an optical microresonator. So an optical microresonator is nothing else than a waveguide that is turned on itself, making a ring like this one. So here you have a ring. And what happens is that inside the ring, you have constructive interference of the light that is traveling. If after one round trip, you have that the phase of the light coming after one trip is equal to the phase of the light that started that trip. So meaning that you have a resonance of the optical resonator each time m, an integer, multiplied by the wavelength of the light is equal to the refractive index times the length of the ring, so the perimeter of your ring. And so if you look now at the transmission of the light through a bus waveguide, you get that you insert the light here, so partially the light that reached this point is entering the microring resonator, and then is exiting through the through port here. And so now if you look at the transmission here, you see that if the wavelength of the light is not satisfying this resonance condition, so you have that the light is passed through. Nothing happens. So you enter and you exit. No problem. But if the light is satisfying the resonance condition, what happens is the fact that the light is entering here, and now you have another waveguide there. And so the light is entering here and then is exiting from this other port. And so you have that the light signal is dropped at this port. But since you are dropping the light at this port here, you do not have any light field at the through port. And so now if we look at the transmittance through the through port, so we see that whenever the wavelength of the light satisfies this resonance condition, you have a dip in the transmission, which corresponds to a peak in the signal collected at the drop port if you are looking now at the intensity of the light through this drop port. And so what you see here, you have a peak. And clear you have a sequence of peaks because of this M here. This is nice, but what we are more interested in is the fact that not only you have this resonance behavior, but what happens is that the light that is trapped inside the microring resonator is starting to build up its power. So you have an enhancement of the power of the light when it is trapped, so when the wavelength corresponds to the resonance condition. So you have a huge field that accumulates within the ring resonator. And in this way, so we enter into a nonlinear regime. You remember that in our perceptron, we need nonlinearity in order to perform the computation that we are interested in. And now here we have tools in order to enhance the nonlinearity of our microring resonator. So going through the microring resonator at resonance. Which kind of nonlinearity we are using? We are using essentially two different kinds of nonlinearity. So the first one is a nonlinearity associated to the generation of free carriers. So here this is a quite unexpected effect. So you are getting a photon that has an energy below the band gap of silicon. And so what you expect is the fact that this photon should be transmitted by the silicon waveguide. But actually what happens is that if the power is large enough, you get that you are starting a new phenomena that is called a new process that is called two-photon absorption process, by which you absorb at the very same time two photons. But now the energy of each one of these photons sum up. And so the sum of the energy of the two photons starts and gets larger than the band gap of silicon. And therefore, you can get absorption of those two photons. And following this absorption, you have the generation of electrons in the conduction band and of holes in the valence band. And those electrons and holes induce a change in the refractive index through the free carrier dispersion effect. And so here you have tools that you can use in order to change the refractive index of the waveguide, of the microring resonator. But then those free carriers do relax down the electrons from the conduction band, do relax down to the valence band. And during this relaxation, you get phonon emission, meaning that the temperature of the silicon is increasing because of thermalization. And so what you see is that these two photon absorption induce on one side free carriers that change the refractive index due to the free carrier dispersion. But on the other side, you get that the thermalization of these free carriers induce a change in the temperature of your silicon. And so you have another change of the refractive index induced by the thermo-optic effect. And so you have those two effects that play a role here, the free carrier dispersion and the thermo-optic effect. And what is nice is the two effects have two different influence on the refractive index. In one case, you have an increase in the refractive index. In the other case, you have a decrease on the refractive index. And so what is even more important is the fact that the dynamics of those two effects are very different. So the dynamics of the free carrier dispersion is fast for us, so in the order of few nanoseconds, while the dynamics of the thermalization, the temperature increase, is slow, in the order of 100 or 40 nanoseconds. And so keep in mind, so when I have a ring resonator, I can induce nonlinearities, so the dependence of the refractive index on the input power due to these two effects. A fast effect due to the free carrier and a slower effect due to the increase of the temperature. Good. So those are the building blocks. So now let us see how those building blocks can be used in order to make something that do a computation. So the first device that I want to show you is a very simple optical neurons. And by the way, so this is the activity of Emiliano. So if you are interested, you ask to Emiliano, not to me, how it is working. So this optical neuron is very simple. So we already saw that the neuron needs to have some input, a place where doing a weighted sum, so a sum of the input through some weight, and then an activation function in order to produce the desired output. So the target, what we want that the neural network does. And so in this first example, so the activation function is nothing else than performed by a photodetector. Because the reason is the fact that the data are encoded in the field, while the photodetector is measuring the intensity of the field. And the intensity of a field is nothing else than the square root of the field. The square, not the square root, is nothing else than the square of the field. And the square is a nonlinear function. The linear function is directly proportional. The square is proportional to the square of the quantity. And so this is the nonlinearity that we are using in this example. And in order to do the sum is very simple. You take two waveguides, and then you merge those two waveguides into a single waveguide. And so what you get here is that the field from this waveguide here interacts with the field from this waveguide there. And depending on the relative phase, here you have constructive or destructive interference. Simple, no? And so this is what we do. And in order to apply weights, since the sum is controlled by the interference, in the interference, you know that the phase play a very important role. And so in order to control the interference, what we do is that we change the phase. And the way we change the phase, the way we train our network, is to use the phase shifter that I've told you. So essentially what we do is that we insert the current in the proper place, and then by depending on the current, so we can control the phase of the field. And controlling the phase of the field, we control the sum. And so in this way, we apply the weight. This is the design of the device. Looks very simple, and indeed is very simple. It's nothing else than a point, which is a grating for us, a grating coupler, a point where we introduce the data. And so the data are coming from this optical fiber here, are entering into the chip. And then here what you have is you have a splitter. So you take this data here in the input and you split the data into 4 different waveguides. And then in those 4 different waveguides you apply a delay. And the reason why you want to apply these delays is very simple. So let us assume that, for example, we have a train of pulses. Each one is 100 picosecond long, so we are working at 10 gigabit per second. And then we send those pulses through our splitter. And then we have that those pulses travel in this waveguide here. The other pulses, the same pulses travel through this waveguide where they see a delay line. So you see that the length of this part here is longer, so they are delayed. And so the very same pulses sequence arrives in this other waveguide here where the delay is longer, and so on and so forth. And so what happens now is that the light is going in, the train of pulses are going there. And so what you get is that now in this point here, you have the actual data, the data delayed, the data delayed 2 times, the data delayed 3 times. And this means that now you can, when you do the sum, so what you are summing is that the data in the present time with a version of the data in the past with a version of the data even in more past, and so on and so forth. And so you are comparing the actual data with the data in the past. And so you can see that during the summation that you are doing, so you are doing the sum between the data in the present and what happened in the past. And now, in order to train your network to achieve, to perform what you are interested to do, what you do is that now you control, by using the current, the phase of all these different pulses sequence in such a way that now here in the point where all the pulses arrive, so you get a different interference profile. And depending on the current, you get a different value in the sum between the delayed version of the input, which are weighted by the phase shift that you are applying. And then you get the detection, where you do the nonlinear transformation of the weighted sum. So these are the dimensions. So this is the dimension of the device. You see, as I was saying, silicon photonics, very small devices. And so the typical size in this specific device is 0.3 millimeter for 1.4 millimeter. Here you see all the wires that are needed in order to insert the current into the neural network that control the weight that you have to train in order to perform the given function. And here I show you an example of what this simple device is doing. So the first example is about a function that is to recognize a given pattern. So we want to teach our network to recognize a pattern. And for us, a pattern means a sequence of data. For example, so we want to train the network to recognize the pattern 1, 0. Out of a bit, a sequence of 1, 0, 1, 1, 1, 0, 0, etc. So we want that the network raise a flag each time the sequence 1, 0 is arriving. And so we play with the network, we play with the weight in such a way that we teach the network to raise this flag. And here is the output. So here is the output. So you see the blue line here is the input. And you see that you have a sequence at a very high speed. So the sequence in this case 16 gigabit per second, high speed. And so you have the sequence of zeros, 1, 1, 1, zeros, 1, 1, 1, zeros, 1, 1, 1, 1, zeros, 1, 0, 1, 1, 0, and so on and so forth. And what we want is that the network, once is trained, should raise a flag each time the sequence that we want, so the sequence 0, 1 appears. And what you see here is indeed that is what is happening. You see here that when you have a sequence of 0, 1, that is not 1, 0, 0, 1, you have that no flag is raised. While when you have the sequence 1, 0, the flag is raised. So the red line here is the output of the network. And each time you have a 0, 1, each time you have the sequence 1, 0, you see that the flag is raised. But if you have a sequence of 1, 0, if you have a sequence of 0, 1, no flag is raised. 1, 0, the flag, 0, 1, no flag, and so on and so forth. And so you see that that very simple neural network is doing something that is not easy to recognize a pattern at a very high speed. And here are the outputs, and when you change the speed, as well as when you change the pattern that has to be recognized. And you see that even a pattern of 3 bits is recognized by the network, with different performance, but still is recognized by the network. Here I show you another example that is more relevant from an application point of view. So you know that each time you send a data through an optical fiber, so you get that the temporal width of this data is increased because of chromatic dispersion. And so it happens that now, if you have a given input, a sequence of 1, 0, 1, 0, because of this broadening of the pulses, you lose the information on when you have a 0 or when you have a 1, after this optical input has traveled through a certain length of optical fiber. And so at the output of your optical fiber, you have a very distorted signal. And the distortion of the signal is due to the what is called inter-symbol interference, meaning that the broadening of the pulses that qualify the 1 mix with the pulses that qualify for 0. And now, since you have a broadened pulse, you are no longer able to distinguish between the 1 and the zeros. And this is a very severe problem because limit the length over which you can send your information. And so what we want to do is that we want to train our network in order to recover for this chromatic dispersion. So we want to train our network in order to recognize from a distorted signal the original optical input. So here is the layout of the experimental setup that is very similar to the one of Professor Segato here. So essentially we have an input, then we have our fibers, and then we have our neural network that recover the distortion, and then we do detect the signal at the end of the network. So here is a sequence of bits. So the blue line are the optical input to the optical fiber, and this is what you see when you record the signal after 100 kilometers of optical fibers. And you see that here, where you would expect to have a 0, you have some intensity, and here, where you would have expected to have a 1, or here, for example, is even more evident. So where you would have expected to have a 1, you have a signal that is lower because of this chromatic dispersion, because of this interference between different symbols. And so if you look now at the histogram of what you would expect to be a 0 and compare with the histogram of what you would have expected to be a 1, you see that you have an overlap between the zeros and the 1. So you are no longer able to recognize in this region here whether you have a 0 or a 1. And so what we teach our network was a very simple, on one side, function, but very important, and to separate those two histograms. So meaning that to take the zeros down and to take the ones up in such a way that now we are able to distinguish the 0 and the 1. And here are the outcomes. So whether you are interested to see the Hay diagram or whether you are interested to see the histograms. And so let's look at the histogram. So here you have the zeros and the 1 at the input of the optical fibers. And here you have the histogram of the 0 and the 1 at the output of 125 kilometers of fibers. You see that you are not able to distinguish between the zeros and the 1. And indeed, the high is closing. After we train our network, you see that now we have trained the network to separate the 1 and the 0, so to recover the information, the initial information. And now the histogram of the zeros and the histogram of the 1s are well separated, meaning that if you look at the eye diagram, so the eye open. Here is another example. Okay, so this is another result of the very same network. So this is the bit error rate. So how many bits are wrong as a function of the different length. You see that for 25 kilometers, even though you have the fibers, so you don't see any effect of the chromatic dispersion because 25 kilometers is very short. But the situation is very severe, is very negative when you travel by 125 kilometers. So the red line here is the bit error rates after 125 kilometers. And you see that the bit error rate is very large. So if you compare the bit error rate with the one that you have at the input, that is the black line here, so you see that the two are very different. And what you see here is the fact that with the optical fiber, you are mitigating this effect. Here is another example, for example, another kind of encoding of the information that is called a PAN4, where the situation is even more difficult because instead of having only 2 levels, 1 and 0, here you have 4 levels, 0, 1, 2, and 3. And so this is 20 gigabit per second, 100 kilometer of fiber. So this is the A diagram before the fiber, and this is what you get after the fiber. So you are no longer able to distinguish the 4 different levels. And this is what happens when you are training, when you have trained your network. You are able now to have one, so the level 0 here, the level 1 here, the level 2, and the level 3. And so this is an application of that very simple neural network, which show you that indeed the network is very good and is very performing. Thanks also to Emiliano that did this great job. But I've shown you a single perceptron. What we can do now is to take more than one perceptron and put those perceptrons together in order to make a network. And so this is what we did. And so we elaborate a network that is called a feed-forward network, where we have different layers of neurons. You have an input layer where you input your data, and then those data are connected to a first hidden layer where they are summed through a weighted sum and then nonlinear transform. And then the output is transferred to a second layer, and so on and so forth. And so this is the kind of networks that are used in the deep learning model. And they are called feed-forward because the flow of the information is only in the forward direction. So the data are inserted in this layer here, and they do reach the output. And now what you do is that you are training the network, so you are changing the weight of each connection, of each synapses between the different neurons in such a way to make that your network perform and achieve the function that you are interested in. And so there are techniques in order to do this training, but let me show you the device. And so here is the device in the package, where you, as usual, you see the very small photonic chip here, and then all the different wires that are needed in order to control the different weights. Here is the idea of the optical network that now we have realized. So in this fit introduce you. So what we are playing here is we are using the nonlinearity of the microring resonator. And then another difference with respect to the network I just showed you is that in the weighted sum, we do not only change the phase, but we are also change the amplitude of the electric field. And in order to change the amplitude of the electric field, so we are using nothing else than a Mach-Zehnder interferometer. So your light is entering here, your optical signal is entering here, is split in 2 parts. One part is propagating this arm there, and the other part is moving in this arm. And along this arm, you have a phase shifter. So you control, again, the phase of the light. And now, by controlling the phase of the light here, so you control the interference in this point. And so what you can do is, so you can have a constructive, a destructive of whatever interference condition that you are interested here, in here. And so in this way, you control the amplitude of the electric field. And then by using this other phase shifter, you control the phase of the electric field. So at the end, you have that the intensity of the field that is transmitted by this component is given by this formula, where you change the amplitude as well as the phase. So you can control in the sum the amplitude and the phase by using this element here. And then you do a very simple feed-forward neural network, which is made by 2 input neurons. So you have 2 signals that are inserted here. Then you have a layer where you do the sum of the 2 input neurons, and then you provide the sum to the microring resonator that is nonlinearly transform the result of this sum, and then you have another layer where you have the sum of the 2 inputs from this microring resonator from that this other microring resonator, and then the sum of the two is again non-linearly transformed in order to reach the output. And then you measure the output, and then you control the weight on the sum and the nonlinear strength of the microring resonator in order to achieve the function that you are interested to achieve. Okay? So this is the device. So this is the circuit. Maybe I go a little bit fast, but here you have one arm, the second arm. Here you do the sum, and then here you have the microring resonator, which nonlinearly transform the result of the sum and provide the information along this line here, where you still control by using a Mach Zehnder and a phase shifter. You still control the amplitude and the phase of the light, so the weight. And then here you have another microring resonator that nonlinearly transform again the output, and then you have the final output here. So this is the circuit, and in this circuit we have a total of 12 free parameters that are optimizing the training process in order to implement the function that we are interested to achieve. And in this example, I show you the use of this network in order to perform to produce a geometrical figure. Here is the output of the trained network. So this is the target square that we want to achieve. Here are the current that we are using in order to encode the data, and this is the output. So you see that we are able to train the network in order to get this figure. Here are other examples. So here we want to make a Z, here an L, here a C, and here a hole, and indeed the network is performing what we are interested to achieve. So instead of having a network where the light is moving only in one direction, so what we can do is that we can use a recurrent neural network, meaning that now the information is stored within the network and is passed back and forward between the different neurons of the network. So in this way, what we achieve is a network that has a memory. And the memory is provided by the recurrence. So the information is stored within the network, the information in the present as well as the information in the past. And so the network remembers what happened before and try to produce an output depending on the actual input as well as of what was the story behind. So the way that we use is a concept that is called a reservoir computing concept in order to implement this recurrent network. And this is particularly specifically important in photonics because this kind of approach is quite easy to achieve. And so here the idea is that we have a reservoir where we have a very complicated sequence of neurons, and each one of these neurons is connected in a random way with the other neurons, in such a way that the information that is coming from the input nodes is projected in a hyperspace that is given by the state of all those neurons. And then we have an output layer, and the state of the output layer is determined by the nonlinear projection through this reservoir. And then what is easy for our application is the fact that now the learning is only performed on the output layer. So only the output nodes are summed by using a weighted sum, and we do control the weights in the output transformation. And so in this way, so we get the fact that now our network has a memory because of the recurrency of the reservoir. And on the other side, so the learning phase is extremely simple because what we have to learn, what we have to change are the weight only, so the connection only of the output nodes. And here is the example of the reservoir computing scheme that we have implemented. It is an extremely simple schematics where you have simply an input waveguide, and then you only have one microring resonator. And then what you do is that you collect the signal at the drop ports. And so what you are doing now, so you are doing a time analysis of your transmitted signal by sampling the intensity at different times of the output signal. And now all these samples are called virtual nodes. So what you are doing is that you are keeping the signal, the input signal, for all the time that you take to record the sampling. And then what you do is that you are doing simply a linear regression of the state of the virtual nodes of all these samples in order to achieve a classification. And so what happens is now the light that is moving back and forth within the microring resonator, so is circulating within the microring resonator, is interacting between himself, and which makes this recurrence between the different virtual nodes. And then you can achieve quite interesting results. I'm going directly to the results because timing is consuming. Here is a first example of the results that we get in this approach. So the idea is simple. So we send the signal in the input, then we let the signal travel through the microring resonator, and then we record the output. Then we sample the light in the output, and then we do a linear regression between those sample output. And we train the network in order that the linear regression gives you the desired output. So here is the first example. So we train the network to do a XOR function between one bit and the previous bit. So what is called one bit delayed XOR. So the idea is to do the XOR function, so the sum between the bit in the present and one bit in the past. And so what we want to have here, if those are two ones, we want to have a 0. If those are two 0, we want to have a 0. If those are 1 or 0 and 1, we want to have a 1 in the output. So this is a very nonlinear function, a logic operation. And here is the result. So look at the result. So this is the bit error rate. So we have 25% of the errors. But this bit error rate stay high up to a certain threshold when we do increase the input power, and so we do onset the nonlinear response of the microring resonator. And once we have that the nonlinearity of the microring resonator is onset, is starting, is effective, then we have this nonlinear transformation. And what happens is that now the bit error rate drops to 0, because now the microring resonator behaves as a reservoir computing. And what you get here is that the very simple device that I've shown you is performing extremely well because you get 0 errors. But this looks a very simple function. And now I show you a very more complicated function. So what we do is that now we do an experiment where we teach our network to recognize a flower among different flowers. And so here in this example specific, so you have a data set where is listed the characteristic of a given flower, that is the iris flower. And what happens is that the iris flower appears in 3 different flavors. One is the setosa flavors, the other one is the versicolor flavors, and the third one is the virginica flavors. And what we teach our network is to recognize whether the iris flower that we have shown is either a setosa or a versicolor or a virginica. And the way we parameterize the different flowers is depending on the width of the sepal, the length of the sepal, the width of the petal, and the length of the petal. And so we teach the network to distinguish whether we have a setosa, versicolor, or virginica. So we encode the data, the width, and length into an optical signal, and then we look at the output. And here are the results. And so what you see here in the results are the linear regression applied to the input, meaning that if we do not use any neural network, so this is the result that the linear regression on the input gives you. And you see that 85% of the times you get the proper classification. So you have that your linear regression is able to distinguish whether you have one kind of flower or another one. And then what you do is that now you teach your reservoir computing system to recognize. And here is the results after you have trained your network. And what you see, depending on the input power, you see that when the nonlinearity starts to get effective, you get the results where you have more than 99.3% of accuracy. And so that means that the network is able to classify the proper color with a 99.3% at the speed of in the order of 400,000 of flowers analyzed per second. And so you see that the network, very simple network, but very performant. Now I have no time to show you those examples. So if I still have 5 minutes, I want to show or more. Yeah, thank you. Never say more here. If I still have 5 minutes, I want to show you where we are in the implementation of this vision.
You have more than 5 minutes.
More than? Okay, thank you.
6 minutes.
Okay, perfect. Since the photonic network is fast, so I can give you 400 times. So I have shown you the integration of the photonic neural network. And now it's time to speak about the biological culture, okay? And first of all, the credits to the experimental platform is actual neurons. So what we are using here are living neurons, so biological neurons. Credits to those who did the work. So here are those who did the great work in the lab. And these are the results. So as you saw in the movie, so the way we use in order to influence the activity of the neurons is to use light. And to do that, so we insert in the membranes of the neurons light-sensitive proteins. And those are proteins then when are illuminated, so they change their conformation. And the change in the conformation opens the ionic channels that exist on the membrane of the neurons. And this change of the ionic channel makes that the local potential is changed. And this change in the local potential activate the neurons. And so this is a very powerful tool that is called optogenetics, by which, by using light, you can influence the activity of the neurons. Not very simple, but so this is a very well-proved technique. So here we are not inventing anything. So we are using something that the others have already invented. Actually, the credit is to Roth that has proved this in 2005. And this actually is optogenetics is a technique that is used to relieve, for example, a impairment in people. Anyway, so we use this technique. So we build up a methodology. And in this methodology, what we do was that we use our neurons and we genetically insert the channel rhodopsin, so these light-sensitive proteins. And now we use light in order to write a given circuit within this population of the neurons. And so what we do is that essentially we are focusing the light in different spots in order to activate of all the neuronal population here only a specific circuit. And here is one of the example where we have, you see in the grain those spots. These are the neurons, so the body of the neurons, and then you have all the processes that are the axon, the dendrites, the connection. And what we do is that we are illuminating specific spot. You see the size of the spots are of the size of the neurons. And what happens is the fact that when you hit one neuron, so then this neuron is sending a signal to a nearby neurons. You hit these neurons, it's sending the signal to these neurons, so on and so forth. And so of all the populations, so we are able to excite only that specific circuit that we are interested in. And so we proved that we are able to insert these light-sensitive proteins, and we are able, by using light, to force a given circuit in the neuronal population. And now what we need to do is that to merge the two fields, photonics circuit on one side and the neuron circuit on the other side. And so this is our setup, tiny as usual. What you see here is a bunch of optical fiber. Here you see a fiber array that is used to take those fibers and then put those fibers in contact with the photonic circuit here. And here you have your photonic circuit. And if you look carefully, you see here a blue line that is moving in the photonic circuit. And this blue light is nothing else than the light that is coming from a fiber is inserted into the photonic circuit and then is traveling in the photonic circuit. And now what we do is that now we want to use, now we want to use this specific setup in order to do the experiment with the neuronal culture that I showed you before. And so what we did was to culture on top of this photonic circuit a population of living neurons. And then we put everything under the microscope because we want to see whether when we shine the light in, so we get an optical signal coming out from the neurons, meaning that we have activated the neurons. And so here is the setup. So you see all the fibers. You have all the connector because now we want to address a specific part of the circuit. And here you see the Petri dish where you have your photonic circuit on top of which the neurons have been grown. Here is an example of a photograph, an image taken on the microscope. I don't know whether you can get, but here you see the small dash, the small spots, gray, are the neurons. And here you see the line, which are the photonic waveguide. And so we grow the neurons on top of the photonic chip. Then we control that the neurons are alive, so we illuminate the neurons, and we market the neurons with a green protein which emit green light when is illuminated, when the neuron is illuminated, and you see that the neurons are indeed there and they are alive. And then in the photonic circuit we have placed some scatterers that are able to scatter the light out of the circuit and to send the light at the neuronal culture. And here is an example. So the fibers, you insert the light here, and then you see all those spots that are illuminated by blue light. And so those spots are used in order to excite the neurons. And then we put the culture on top of our photonic circuit. And what you see here is the culture, so the neurons that are alive. And then you see all those blue spots that are the blue spots coming from the photonic circuit. And then whenever the spots hit a neuron, so then the neurons shine red light. And here you see the red light that are produced by the neurons that are illuminated by the photonic circuit. Here is a blow up. You see this is the body of one neuron, and this is the body of one neuron that have been illuminated by the blue light. And so what I'm showing here is the fact that now we are able to excite our culture. Is this culture of neurons alive? Is this culture of neurons electrically producing a signal, an electrophysiological signal? And so the idea here is to try to measure the electrical activity of our culture of neurons. And so what we did was to grow the neuronal culture on top of a matrix of electrodes. And in this way, so we have a matrix of electrodes that are able to measure the electrophysiological signal, so the signal coming from the neurons. And then we stimulate the culture by pattern light, and this is the result. So this is in color code the firing rate of each one of these cluster of neurons that have been contacted or are in contact with the different electrodes. And this is what you see when you illuminate the whole population. So you see that the activity depends whether you have neurons on the electrodes or not. And this is what happens when you are illuminating only one specific part. And you see that instead of exciting the whole neuronal populations, so what you are exciting here are only those neurons that are forming the circuit with a specific place which you have excited. So in conclusion, so I've shown you the data about the photonics and the biological culture and the essay that we are trying to develop in order to make this hybrid artificial network. And so we are on the way to realize our vision. Still, there is a long road ahead to move from those experiments that we are running in vitro to in vivo experiment and eventually humans in order to realize the vision to be able to support malfunctioning brain sectors. So here I would like to acknowledge the supporting projects and the different agencies that are supporting this activity on neuromorphic photonics. And by saying that, I'm close and thank you for your attention. Yes.